Hello, hi everyone. Welcome to the Student the Brand. This is your Sir. Sir. Today we are going to discuss about laws of motion. Laws of motion. Okay. So in this topic, we will discuss about laws of motion. Grade 11. Laws of motion. Laws of motion. So actually Newton's laws of motion. Newton's laws of motion. Okay. Newton's laws of motion. So here in the chapter we will discuss about inertia. First of all, inertia. So what is inertia? Inertia is nothing but tendency of the body to remain stay in the state of rest or motion or direction. Okay, unless external force acting on the body, the body does not move from its position. Okay, so inertia is nothing but unless external force acting on the body does not change its position. Okay, tendency of the body to remain stay its state. So like we can say there are three are there: inertia of rest, inertia of motion, inertia of direction. Okay, so inertia of rest, inertia of motion, inertia of direction. So what is inertia of rest? Inertia of rest. So unless until we apply force on it, the body does not move from its position. Okay, suppose you can say a book is staying on the table. Okay, like an object is placed at one position. So until you apply, or best example you can take the fan. Okay, until you on the switch. So anyway, after that only current will pass. So then it will move. Otherwise, a book is there on the table. Okay, so without your external force, the body does not move from its position on its own. Okay, on its own. So it does not move by its own, right? So that is called inertia. So there are three types of there: inertia of rest, inertia of motion, inertia of direction. Inertia of rest. So what is inertia of rest? As I said, unless external force acting on the body does not move from its position. That is rest position. Okay. So best example, fruits are there. Okay. So to the tree fruits are there. If you shake the branches, the fruits will fall down. The branches comes under movement. Okay, so fruits are ready to no fruits are staying the same position, so branches are shaken, then automatically it will fall now. And the best example, so caroms are placed one by one. Okay, if you hit the bottom carom, so remaining all caroms will fall. Okay, because inertia of rest. Okay, and one more thing, if you throw the ball also, so in moving car, so because of inertia, okay, so it is trying to same in the same position. Okay, so and one more thing, one more example we can take. One more example. So a body is there, right? So unless external force acting in the body does not move. So that example we can take. And one more thing, when you are sitting in the running bus, suddenly the bus, so the driver applies brakes. What happens? So we may fall back or front. We fall backward. Yes or no? So why? Suddenly our so upper portion will be staying in the same position. So whereas lower portion trying to come to the stop. So that's why okay. So we will fall forward. Okay, and suddenly it start. Okay, bus is starting. Then what happens? So our body is staying in rest position. So so bottom position it trying to move forward. Then we will fall backward. Okay, so that is very important. So make sure that you apply. And one more thing, so you can take one more dust particles, right? So to the dust particles are there, or you can take the carpet. Okay, so if you beaten with stick, So carpet will trying to move, then the dust particles are trying to stay at the same position, then dust particles will come forward. Okay, so it falls down, then carpet will comes under motion. Okay, so that is about inertia of rest. And coming to inertia of motion, so fan is continuously rotating, right? So once you are, so automatically fan continuously rotate. So if you off the switch, even you off the switch, still the fan continues to rotate. Okay, it will be until certain time. Okay, so and one more thing, long jump person, he will run certain distance. Okay, so to take inertia motion, automatically when he is in motion, so it continues forward. It continues, then automatically will jump. Long jump persons like that. And that is about inertia of motion. Inertia of motion. And coming to inertia of direction. Inertia of direction. So generally when person is getting down from the running bus, so he has to move in the same direction until certain distance. Otherwise, so he will fall, right? So it continues the same motion. Understood or not? And one more thing, so while you're taking the turn, if suddenly driver job, so rotate the wheel, automatically what will fall away from it. Because we are trying to move in the same position, so when suddenly turns, so we'll move in a particular direction. Inertia of direction. One more thing, so you can see cycle wheel. So when cycle is moving on a rainy season, the water droplets you can see it moves along the tangential direction. Even if you take a stone and tie at the end of the thread and rotate and whirl like this, then what happens? If you leave, it moves along the tangential direction. Understood or not? So like this. So this is about inertia of rest, inertia of motion, inertia of direction. Inertia of rest, inertia of motion, and inertia of direction. And coming to the force. So a push or pull of an object is called force. Okay. When we apply force on the object, then only the object moves from one point to another point. Without applying force, the body does not move. Yes or no? So when we apply force on the object only, the body moves from one point to another point. So from one position to another position, right? So a push or pull of an object is called force. Okay. An external agency making the object to move from one point to another point. So there are two types are there, contact forces and non-contact forces. Contact forces and non-contact forces. Coming to contact forces. So by contact only the force will act. Example, frictional force. When you are walking, friction will be there. When we are moving forward, so ground will apply on us in a opposite direction. By contact only, the force will act. Okay. Fluid drag. So in liquids. And one more thing, muscular force. By using our muscles, we lift our object. We lift the objects. So we will lift the weights. By contact only, the force will act. And tensional force. When you suspend the object, automatically force will be there. Okay. So these are the example. Frictional force, muscular force, tensional force, contact force example. And coming to the next one, non-contact forces. Without contact, the force will act. Example, electrostatic force, gravitational force, magnetic force. Without contact only the force will act. Best example, magnetic force. So I hope you studied everywhere. Okay, magnetic force right from lower classes onwards, 6th, 7th, 8th, 9th. So even 10th, magnetic effects of electric current. Now we are studying in 11th class. Okay, still in 12th also it is there, magnetism. Okay, so there are so many topics. Like everywhere we will use this word, magnetic force. At a certain distance only, the magnet will attract. So if you are taking this one, this is north, this is south. So Two dissimilar poles will attract, two similar poles will repel. North north repel, south south repel, north and south attract, south and north attract. Two dissimilar poles will attract, two similar poles will repel. At certain distance only, without contact only the force will act. Without contact only the force will act. Understood? Our magnetic force. And coming to the gravitational force. Gravitational force. If you drop the object, always it moves towards earth center. Gravitational force. Okay. So at a distance only the force will act. Non-contact force. Okay. Contact force and non-contact force. Contact force example already we discussed about contact force. Coming to non-contact force. So magnetic force one example. Gravitational force. So if you throw so many times, if you throw the object upward direction, if you throw 100 times, 200 times also, the body again and again it comes towards the earth center. It falls down. By that. So notice some motion. Understood or not? I hope it is very clear, right? So gravitational force. Next, electrostatic force. Electrons between the charges. You take a comb and comb it. And take it near to the piece of papers. Take comb and comb it. Take near to the piece of papers. It's getting attracted. Okay, pieces of papers will be getting attracted due to electrostatic force. And you take two balloons, one balloon and another balloon, and rub each other. Okay, so you can take one balloon and rub, and take near to the uncharged balloon. So unrubbed balloon. Then so by this balloon, that balloon getting attracted, even at certain distance. Okay, so you can take the plastic pipe and rub with the cloth and take near to the balloon. Automatically it will getting attracted or repel, depends. Okay. So like uncharged balloon, charged balloon, electrostatic force. Electrostatic force. I hope it is very clear. These are non-contact forces. Non-contact forces. Coming to that, so we can say balanced force, unbalanced force, balanced force, unbalanced force. So if two forces are acting on the body, so equal in magnitude but opposite in direction. Okay, equal in magnitude but opposite in direction. So if I am taking this one, so this is the body, this is the object, Okay, object. So an object, two forces are acting. On the object. So like this. So this is one force and this is one force. Okay. So F1 and F2 I am taking. Two forces. Two forces are acting on the body. Those two forces are equal in magnitude but opposite in direction. Equal in magnitude. Suppose if you are taking 5 Newton. So this is 5 Newton and here also 5 Newton. Then what happens? So both forces are equal in magnitude but are acting opposite direction. So both are balanced force. So both are balanced each other. Then body does not move. Okay. And second thing, unbalanced force. So suppose here I am taking 10 Newton and here 5 Newton. Then in which direction it moves? So in which direction 10 Newton force is acting? So along the direction the body will move. Understood or not? Yes or no? Is it clear? So unbalanced force. And coming to the linear momentum. So linear momentum is nothing but linear momentum. So linear momentum is denoted with the letter P. Okay. It is a vector quantity. P bar equal to mass into, so m into v bar, mass into velocity. If your P equal to mv. Okay. So momentum, linear momentum. That is SI unit of mass is kg. So SI unit of velocity is meter per second. Meter per second. SI unit of velocity is meter per second. Kg meter per second. The product of mass and velocity is called linear momentum. The product of mass and velocity is called linear momentum. And coming to the law of conservation of linear momentum. Law of conservation of linear momentum. So momentum before collision. If two bodies are there, suppose I am taking two bodies. So here you can see. So two bodies are there. This is a body M1, U1, and this is one more body M2, U2. And after collision, so both bodies are collide each other. So it is moving M1, V1, and this one is moving M2, V2. M2, V2. Momentum before collision is equal to momentum after collision. Momentum before collision equal to momentum after collision. M1 U1 plus M2 U2 equal to M1 V1 plus M2 V2. Understood or not? Momentum before collision equal to momentum after collision. And coming to the one more point, even kinetic energy also. Law of conservation of kinetic energy. Kinetic energy before collision equal to kinetic energy after collision. Half m1 u1 square plus half m2 u2 square equal to half m1 v1 square plus half m2 v2 square. Okay. So next one. So we'll discuss about impulse. Impulse. Impulse is nothing but large force acting in a short interval of time. Large force acting in a short interval of time. Okay. Large force. Just so you can see, if you take a bat, so suddenly ball is coming, so you are hitting with a large force. Okay. And you are slapping like someone. You will not slap like this, right? When you are angry, when you are getting angry, that time. So like this. Understood? You lose so much energy. So much energy you'll use and you will slap like anything. So you are using large force acting in small interval of time. Only less time, so large force acting. Understood or not? So even you are throwing the bottle, so you are using large force. It is fractional seconds, it's applying force. Impulse. I equal to force into time. Impulsive forces. Okay. So like that. And the next one, so we'll discuss about Newton's laws of motion. That is Newton's first law, Newton's second law, and Newton's third law. So what is Newton's first law? What is Newton's first law? So it defines the inertia. Newton's first law defines the inertia. So I mentioned in the starting of the class, inertia. So inherent property or tendency of the body try to stay in the same state, or unless external force acting on the body does not change its position. So inertia, three types: inertia of rest, inertia of motion, inertia of direction. Inertia of rest, inertia of motion, inertia of direction, like three. Understood or not? And the next one, Newton's second law. The external force acting on the body, is equal to the rate of change in momentum. The rate of change in momentum. So coming to Newton's second law. So second law directly. Newton's second law. So Newton's second law. That is, so external force acting on the body is directly proportional to change in the rate of change in momentum. The rate of change in momentum. That is nothing but final momentum minus initial momentum. mv minus mu by t. Okay, so with respect to time we are taking now. So F equal to K into M, I am taking common. V minus U by T, that is nothing but T. F equal to, what is this one? K into, so acceleration. So K anyway equal to 1. So F equal to K is a proportionality constant. So here I am taking K is a proportionality constant, that is 1. That is equal to 1. Understood or not? So that's why F equal to ma. The net force acting on the body is equal to mass of the body and multiplied with acceleration of the body. F equal to ma. F equal to ma. Understood or not? The rate of change in movement also we can take. Is it clear? Right, next one. So coming to third law, Newton's third law. Every action there is equal and opposite reaction. For every action there is equal and opposite reaction. So if you are taking this Newton's third law, Newton's third law, Newton's third law. Understood? For every action there is equal and opposite reaction. This is A and this is B. So this is the force A on B. So this is the force B on A. Both are acting opposite direction. Understood or not? For every action there is equal and opposite reaction. Is it clear? Understood? FAB is equal to minus BA. So direction is different. Remains everything is correct. So that is about Newton's first law, second law and third law. Okay, next one, equilibrium of the particle. Equilibrium of the particle. The net, the vector sum of forces, the vector sum of all the forces are acting on the body is equal to 0. The vector sum of all the forces acting on the body is equal to 0. Then we can say the object is in equilibrium. The object is in equilibrium. So coming to Lami's theorem. Lami's theorem. Okay, so this is the Lami's theorem. Now you can observe. So this is the force is acting F1. So F2 and this is F3. So on F1 this is alpha, beta and gamma. F1 by sin alpha, F2 by sin beta and F3 by sin gamma. So alpha, beta, gamma. This is the gamma. Okay, so F1 by sin alpha, F2 by sin beta, F3 by sin gamma. That is Lami's theorem. So I hope you like it. So if you like the content, if you like the channel, please do like, share and subscribe to Student the Brand. This is your sir from Student the Brand. So thank you so much for joining and attending and listening my class. So we'll see you in the next class. Signing off. Thank you.